In this video, we're going to be working through some real exam problems from past papers. All right, find the roots of the equation z plus 5i cubed is 4 plus 4 root 3i, giving your answer in the form r cos theta plus I r sine theta minus 5. R should be positive and theta should be between 0 and 2 pi. Okay, well, this is basically a standard cube root problem, except for the fact that after we found our solutions, we'll just have to subtract 5i. So this shouldn't be too much harder than just find the cube root of 4 plus 4 root 3i. So let's start with the fact that z plus 5i cubed is, well, let's get this into modulus argument form. So the modulus, we do 4 squared plus 4 root 3 all squared, square root that, and it's 8. And what's the argument? Well, little sketch here, 4 along, 4 root 3 up. Inverse tan of 4 root 3 over 4 is inverse tan of root 3. Good one to know, it's pi by 3. So that is pi I by 3. So that's the thing that we want to find the cube root of. So recall that for cube roots, we just need to find one root and then multiply that by 1, by omega, and by omega squared, where omega is the first cube root of 1. So let's go ahead and cube root what we have. Z plus 5i is, well, the cube root of 8 is 2, and then we're just going to be dividing that by 3, so pi I over 9. Okay, what are we multiplying this by? Well, we just need to solve our omega cubed equals 1, which is e to the 2 pi I, and so our omega is e to the 2/3 I over 3. So we're just taking this stem and we are multiplying it by that. So I guess we could just, we'll just do them on the next line, just to give us some room. So our first number is just 2e to the pi I over 9, and then when we multiply that by that, we just need to keep the modulus the same, add the arguments, so that is a 9th pi plus 2/3 pi, so that's 7 I pi over 9. And then we multiply it by omega squared, which just means multiplying by e to the 4 pi I over 9, and that gives us 2 e to the 13 pi I over 9. So here are our 3 roots of z plus 5i. We'll just remember to subtract the 5i at the end. So what do we have? We want it in r cos form. So this, clearly the modulus is 2, so r is 2. So it's r cos pi over 9 plus 2 I sine pi over 9, and then it's same for this, 2 cos 7 pi over 9 plus 2i sine 7 pi over 9, and so on. So all we need to do to get it in that form is simply subtract 5 from the imaginary part. So our 3 roots are simply keep the real bit the same in each case. And to get it the exact form, they want us to pull out an I, so plus I, and then they want 2 times sine of theta minus 5. And so on. That takes a minute to write out, but pay attention to the form they ask you to write your answer in. It's worth it to get all the marks. There are our 3 solutions. Okay, next question. Use De Moivre's theorem to show that cos 5 theta is all of that stuff. Okay, remember our we'll come on to B in a moment. Remember for this one, we're going to use De Moivre's theorem basically, and that is that cos 5 theta plus I sine 5 theta by De Moivre's theorem is the same as cos theta plus I sine theta to the power of 5. And so all we need to do is expand this and find the real part. The real part of that will be cos 5 theta. So take a deep breath and expand it all. So that's cos to the 5 theta. 5 choose 1 is 5, so 5i cos to the 4 theta sine theta. It's really worth practicing expanding stuff like this. It's so helpful to be able to do this in one line instead of kind of 5 lines. Let's see if I can actually do it now. 5 choose 2 is 10. So, it's this one's squared now, so it's minus 10 cos cubed theta sine squared theta. Then it's this one cubed, so that's minus I. So minus 10 cos I cos squared theta sine cubed theta. Then it's this one to the power 4, so we're back to positive. So plus 5 cos theta sine to the 4 theta. And finally, what is that? That's just plus I sine to the 5 theta. Okay, we definitely don't want to waste too much time, so we're just going to go straight to what the real stuff is there. Cos 5 theta is, well, this bit's fine, that's just cos to the power of 5 theta. This one here, we want it all in coses, so I'm going to keep my cos cubed theta, and I'll replace my sine with 1 minus cos squared theta. This is imaginary, so I leave it, but I do want this one. I'll keep my cos theta, and I'm going to consider sine to the 4 theta as sine squared theta squared. Here's sine squared theta, and here it is squared. So let's just start expanding. Cos to the 5 theta, what do we have? Minus 10 cos cubed theta plus 10 cos to the 5 theta. And this one, when I expand it, okay, this one, the first term is 1, so it's going to be 5 cos theta times 1. The next term, this would be minus 2 cos squared theta. Times it by that, and we get minus 10 cos cubed theta. The final term would be positive cos to the 4 theta, times it by that, and we get plus 5 cos to the 5 theta. Grouping everything together, how many cos to the 5s? We got 1, plus 10 is 11, plus 5 is 16. So 16 cos to the 5 theta. Now the cubes. Minus 10 is minus 20, minus 20 cos cubed theta, and all that remains is the plus 5 cos theta there. And there's our answer as required. Great, ready for part B. Hence, obtain the roots of that equation. All right, so what on earth has this got to do with this? Well, if I write it out for you there, you can see that this here looks suspiciously like this if we double it and if x is cos theta. So let's go ahead and do that. Let's say let x equal cos theta. All right, what does this line become? And I'm going to pull out a 2 from that as well, because when I pull out a 2, I'm left with 16 cos to the 5 theta minus 20 cos cubed theta plus 5 cos theta minus root 2 equals 0. But look, we know what that is. It's cos 5 theta. So 2 cos 5 theta, if I add the root 2 to both sides, is equal to root 2. Okay, cos 5 theta is root 2 over 2, and this is relatively easy to solve. We have 5 theta is equal to, well, the first solution there is pi over 4, and the second solution for cos is 2 pi minus that, which is giving us 7 pi over 4. Since we're going to be dividing by 5, I do want 5 solutions here, so we'll keep going. So I add 2 pi to this one, and I get 9 pi over 4. I add 2 pi to this, and I get 15 pi over 4, and one more is going to be adding 2 pi onto this, and that's giving me 17 pi over 4. So dividing by 5, I've got my values of theta. So pi over 20, etc. All of these over 20. And so the solutions to this equation, which are x, are just cos of all of these. So cos of that, and look, that's the form I wanted, right? We want the roots of this equation in the form cos of stuff, where q is a rational number, and it is, because look, our solutions are cos of, let's really make it exactly the same, 1/20th pi, and cos of 7/20ths pi, and so on until we've got all of them. So there are our 5 roots of this quintic equation. By the way, aside from the exam, isn't it strange that we have this quintic equation that you can solve trig for? Let's just take a look in GeoGebra just to see what this interesting equation looks like. So here it is, and you'll notice it's just quite an unusual quintic equation where it just so happens that all 5 roots lie between -1 and 1. One of them actually is 1, by the way, but that's why we could use this technique, because it happened to have all of its wobbles happening between -1 and 1. Okay, let's do one more exam problem here. So show that the sum from 1 equals n of z to the 4r is all of this. Okay, so this looks, okay, it's nothing to do with complex numbers for now. This is simply a geometric sequence. Well, I guess let's just be careful. So when r is 1, we have z to the power of 4. So a is z to the 4. And then each time we increase r by 1, the next one is z to the 8. So the ratio is also z to the power of 4. And there are n terms, so n equals n. So it means the sum, so sum of a geometric series, is, it's not to infinity, is it? No, from r equals 1 to n of z to the 4r is the first term, so that's z to the 4, multiplied by the ratio to the power of n, so that's z to the power of 4n, minus 1 all over z, the ratio r, z to the 4 minus 1. Now, it's not quite what we have here, and I think we'll see why we want it in this form later on. That looks like it's gearing up for some kind of 2i sine something form. So we can get it in that form. Let's just expand first. So that's z to the power of, well, 4n plus 4 minus z to the power of 4. And the only difference between what we have and what they have is that everything's been divided by z squared. So this top one divided by z squared, we knock 2 off the power, so 4n plus 2. We knock 2 off the power here, off here, and off here. And we are done with part A. Okay, by letting z equal cos theta plus I sine theta, show that as long as sine 2 theta isn't 0, this holds. All right, so this to me just looks like the imaginary part of our sequence here. Here's why. We know something about this sequence here, and specifically we know that we have this form for our answer. Now this sequence there, what is that? That is z to the 4 plus z to the 8 plus z to the 16 and so on, all the way up to z to the 4n. But if z is cos theta plus I sine theta, then that is the same as cos 4 theta plus I sine 4 theta. And the same with 8, cos 8 theta plus I sine 8 theta, and so on. So the sum of sine 4r theta is just the imaginary bit of this sequence. So we are looking for the imaginary part of this. So to get an imaginary part of that, well, we just need it in some form where we can tease apart real from imaginary. Now, the first thing I'll observe is that this down here, z squared minus 1 over z squared, that is 2i sine 2 theta, which looks great because that's where I'm heading to here. Now, there's a temptation maybe to do something at the top, maybe some force factorizing, but I'm not going to. And I'm not going to because I'm kind of seeing the things that I already have here. I'm seeing a 4n plus 2 and a 4n plus 2, and I'm seeing a 2 here and a 2 here. So let's not do any force factorizing, but let's simply say that that top z to the power of 4n plus 2, that is cos of 4n plus 2 theta plus I sine 4n plus 2 theta. And that z squared is just cos 2 theta plus I sine 2 theta, but minus for both. So minus cos 2 theta and minus I sine 2 theta. And all of that is over, we've now just established, 2I sine 2 theta. Okay, well, all I need to do to get that denominator perfect is to divide the top and bottom by I. So dividing by I, just got to be a bit careful. Dividing by I is the same as multiplying by I and then multiplying by minus 1. So if you multiply this one by I and then by minus 1, we have minus I cos 4n plus 2 theta. This one we can just cancel the I, right? We've just got plus sine 4n plus 2 theta. Dividing this one by I, same as multiplying by minus I, so that's plus I cos 2 theta. And then here we're just cancelling the I, so that's that. And all of that is now just over 2 sine 2 theta. Okay, and the result we wanted was simply the imaginary part of that. So the imaginary part of this series, from r equals 1 to n of z to the 4r, is simply the imaginary part of this. So it's this bit, let's take this one because it's positive, it's cos 2 theta minus this stuff here, cos 4n plus 2 theta all over 2 sine 2 theta, and that's exactly what we needed to show. So we are done with that. Okay, hopefully that was useful looking through some real exam problems. Have a go at some yourself, and I'll see you in the next video.